Ladies and gentlemen, welcome to November 9th, the best physics class ever. Simulated echo. I'm losing it. I'm in class. I gotta teach, okay? Get out of here, will you? Sheesh. All right, whatever. Oh, that's not what you want to see. Quiz summary. 46%. There's the averages if you're interested. We'll worry about that later. Sheesh. All right. Okay. Yeah, I'm just in a foul mood. I'm tired of online learning and online lack of learning and online hell. That said, we're going to kick ass. We're going to do problem 30.23. And let's learn as much as we can while we're here. All right. Good, Sean. Good. I wish I could physically go in your spam folder and never return. Just be done with this hell. But instead, we're going to do question 30.23. The most intense, awesome physics problem ever. Okay. So we have a circuit. I'm just drawing it out here. We got a switch. So last time we did a bunch of demos to try and get a feel for this. And actually, I realized something. I need to draw this a little bit over here. This black marker's kind of crapping on me. Let's get another one. There we go. So the obvious thing to do here, I guess I might as well show you what I'm doing live here. If you've had a chance to look at the problem, there's me. So the first thing that I'm going to do is draw pictures, right? All right. And so we've got an inductor, a resistor, and a battery. And then I'll do another picture. Okay. Oh, this is a 3R. For some reason, I chose to use 3R here. Whatever. We can use that. Okay, so the resistance here is 3R. And to be clear, the pictures that I'm drawing are the T equals, do you remember what these were called? The order of these? You probably do. 0 minus, 0 plus, and T equals infinity. Sometimes we call this last one the steady state. And this one is just after switch closed, or just after the change. Sometimes this is called long time after. So these are the phrases that you might see in a problem statement. If you hear steady state, that just means T equals infinity picture. If you hear just after, that's the 0 plus. That's supposed to be a plus there. 0 minus would be this case here, things like that. So this is just before switched. So to be clear, this is just after switched. This is just before. All right. Now, what piece of information? We're doing an RL transient. We have resistors and an inductor in here. What is the piece of information I need to get from the 0 minus picture? Do you remember?
Initial current, initial
exactly
across the resistor.
Because an inductor preserves current. So it is going to keep the same current. Well, in this case, what's the initial current with the switch open?
Nothing.
Nothing. So as we go over here, that's going to be the same. That's how you get this started, because if you don't have that piece, you're lost. This is very different from an RC transient. In an RC transient, capacitors preserve voltage. So basically, that's the main difference here. With the capacitor problem, we started by bringing over voltage. With this, we bring over the current. All right, how does that help? What can I then learn about this circuit?
The current is still 0.
Yes, so what else does that tell us?
Voltage is 0.
Across
The resistor.
Yes. If current is 0, I want you to immediately be thinking, okay, voltage across resistors is 0. All right. So what does that tell us?
All the voltages across the inductor.
What is that? Yeah.
Voltage equals E.
So clearly, if we're going to do a loop here, right? Think about it. If there's voltage positive E on this side, when I go down, I'd have to get a negative E. So again, this is voltage E opposing the current flow. This makes sense. All right. Then what's the next step? What do I remember? In the T equals infinity picture, what are you supposed to remember?
The voltage across the inductor is 0,
Um,
or the current across the inductor is 0.
yeah, I would go with that because inductors, it's good to start with current. I think you're right in this case, but in steady state, I would start with inductor. This is the reasoning I like to use. Acts like a short, meaning it's a short circuit or it's a bare wire, which, as Trey just pointed out, there's going to be no voltage across it. That's great. So let's say there. So this is the reasoning that I go through to get to that. And it sounded like Trey was saying that in his own way, which is great. But yeah, basically, we know that the voltage across the inductor is 0 because it's a short circuit. So then what does that tell us down here about the resistor? Somebody else.
It has all the voltage.
Yep.
And the current's E over 3R.
Three R because this resistor is 3R. Excellent. So now if we go back to our problem, this is basically the strategy you do with all these transients is you draw first, then reread. Sort of like doing an FBD, then rereading. Okay, so actually we just did this and we just did this. So we've handled both of those, right? So initially no current flows. At the end, a lot of current flows. Got it. And then how long does it take for the inductor to energize to 65% of its steady state value? Okay, this is you could argue it's a poorly worded question. When you read this, it's unclear what they mean. If it says to energize, what does that make you think of? What parameter?
The current flow.
You could think of current flow. What's another parameter you might think of?
The voltage across dropping.
Oh, you could talk about voltage. Okay. What's another one?
Energy.
Energy. And it's unclear which of these it is. These ones are pretty straightforward. We could talk about this. I would argue this one maybe isn't so great, but it's unclear whether I meant current or energy here. Now, as written, when I see energize, I'm going to guess I meant U here. So just to be clear, we could solve for both of them, right? Let's do both of them. Now, do you guys know any equations? Let's go back to capacitor land for a second. Let me get this off the screen. So if we pretend we're doing RC transients again, we could find the voltage and the charge really quickly. How would I get the energy as a function of time? I'd plug it into U equals 1/2 QV. So let's review our inductor equations now. And maybe you don't know this, but the energy with an inductor is 1/2 mv squared. What? Inductance is like mass, current is like velocity. Anyways, so this is the induction energy equation. All right, more on that analogy later in the next chapter. But yeah, so there's going to be an analogy for mass and acceleration and spring constant for all these terms we've been playing with all semester. It's pretty cool when we get there. Anyways, in this case, you could see that we could basically figure out I as a function of time and then plug it into this equation. So let's go ahead and do that. How do I get I as a function of time? In this case, that's going to be I final plus I initial minus I final times e to the negative t over tau. What is tau for this problem?
RC or L over R?
Exactly. So L over R, in this case, it's going to be L over 3R because the resistance for some weird reason was called 3R, whatever. Doesn't matter. Excuse me. All right. And then I initial in this case is what value?
Zero.
We get it from which picture?
The second one?
Yep, the 0 plus. Not this I0, this I0. All right, so that's going to be good. I final is going to be E over 3R. E over 3R for both of those. All right, and so now we've got this. Whoops. And did we solve the problem? Let's see. What do we need to do here? All right. How do I get this job done? I did not solve it yet. How long does it take to reach 65% of its energized state? What do you think?
Would you replace I of t in that equation with 0.65 I and then solve for time?
Okay, so he's saying right here, could I just say this is 0.65? What do you mean by I?
My bad. I might not be reading this correctly. It could be not I.
I will be I total. Then wouldn't it be E over 3R?
That's one way to do it right there. And so remember, I would say instead of I would say I max, right? So 0.65 of the maximum value, right? And so that would mean, now that's if we're talking about reaching 65% of the current. The other option would be if we wanted to get 65% of the energy first I would plug this equation into here, and then I would say U of t equals 65% of U max. And so I'll show you both of those here. Now, in this case, let's go to the solution and see what I actually wrote up. I don't know if I did energy or current there. Let's see. Wait, this is chapter 30. Ugh, just seeing that problem is torture. All right, that's still in. Oh my gosh, this is a long solution. All right, so this is where we were at right there. So it looks like, according to this, my intuition's thinking I meant energy seems to be right because it said energize, so that implied energy. So then we would have to do this way. So take a look here, see if this makes sense to you really quick. So we found I as a function of time. We plug that into U of t. Notice we get some junk out here. And so at this case, notice this is a cool trick I might mention here. Just double check what happens when you plug in t equals 0 and t equals infinity. So again, every time you write an ugly equation like this, check t equals 0 and t equals infinity. The reason you check those is you could see if you accidentally screwed up plugging in what initial and final were up in here, right? It's very easy to accidentally switch the final with the initial by accident or write them backwards or something. So if you check t equals 0, if I plug in a 0 here, e to the 0 is 1. 1 minus 1 is 0, which means there's no energy at time equals 0. Well, that makes sense with our picture. It wasn't really, it was going to ramp up to some energy. If I plug in t equals infinity, e to the negative infinity is 0. That means after an infinite amount of time, I should have the full energy level. So this makes sense. That's what this line is doing right here. All right, so then we say 0.65 of the U max, and notice all this crap out front that I'm putting a green star through here, all that blob right there, that's just U max. So you can see it again. Let's clear that up. So that big blob out front is U max. Let's maybe circle it in a different color here. So that's all U max. And so notice a lot of times all those constants drop out anyways. And from there, you take a logarithm of each side and you're off to the races. So let me see if that solution makes some sense here. And then I said, watch out, remember tau is L over 3R. What do you think? I know you've got the solutions yourself, but I'm just kind of giving you a second to look at that. Just let me know if you see anything in there. If you have any questions about any steps, I'll pause for just a minute and see. All right. I have no idea. I'm going to assume that was okay. I don't know. Or, all right. Let's keep going. Let's go on to the next one. Let's just do as many of these problems as we can and get this class over with. Let's just try the next problem. Let's just go in order. Let's not think. All right. Just try and keep this train moving here. Okay. 30.24. Let's take a second to work on it. You could chat with anybody you want. And then we get to do the delicious problem next. I'm going to draw it up. So if you have a friend in the class, you could send him a chat message, say, this is what I think, or whatever. Anything you could do to try and make it more interactive is better. Okay. Hmm. Ooh, this might be interesting. So we're told that R1 equals R2 equals R3 has the value R. And that battery's got some, okay, got it. Okay. Oops. There we go. All right. So while the switch is open, what's the current in R1?
Zero.
All of it, right?
R1. So look, the switch here, yeah,
All of
it's
it.
all of it.
What's
Takes
the-
this inductor out of it, right? But basically, this is still a loop. We still have a loop, right? So there's still going to be current flow. So it's a trick, right? Just because the switch is open doesn't mean there's no current. In this case, the switch is only for the inductor. So in this case, what's the current? They all have the same resistance.
E over 3R?
Yes, because they're in series. So you just add them up. Got it. Okay. And then, so this would be like the T equals 0 minus picture, right? So now what's the next part? Okay. So it says the next question, let's just show it on the screen. Closed for a long period of time, blah, 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 blah. What are we looking for in this case? T equals 0 minus, 0 plus, or infinity?
Infinity?
Infinity. Yep. And then the other word for it was what type of state? You remember?
Steady state.
Steady state. Excellent. So those are the two. And notice here's the where I start using that term, steady state. You're going to see that a lot in electrical engineering. Okay, steady state. All right. Nice job. All right. And so in this case, we don't need, notice this problem is asking us about the steady state only, and then we're on to the next guy. So let's just keep rocking here. So let's not worry about the 0 plus picture. And then remind me, what does the inductor look like in steady state?
A short?
A short. So in this case, we could replace this with a short, even though it's not really a short, it's an inductor. So that's a short in steady state. So what does that do? Now what's the current in R1?
Is it E over 2R?
Exactly, because now all of the current is going to flow in this path, right? Now you could say, shouldn't some current go this way? Maybe a microamp or a nanoamp, but in general, because this has essentially zero resistance, that means all of the current is going to flow that way. So in this case, this one gets cut out of the loop in steady state. So we see that the current should be E over just 2R now. What's the current through resistor 2?
Effectively 0.
Effectively 0. What's the voltage across resistor 2?
Also 0.
Yeah, what's the voltage across resistor 3?
E over 2.
E over 2. Take the current times the resistance. E over 2R times R would give you E over 2. Cool. And so there's probably going to be a question either on a quiz or a final where you get a picture like this. And instead of having to figure out all parts of it, I might either ask you about the steady state or just after the switch is closed. So basically, expect a question either on a quiz or a final where I ask, hey, what's up with the t equals 0 plus picture or the t equals infinity picture? Except I won't make it that easy for you. I'll say these words just after the switch is closed, or a long time after the switch is closed, or in steady state. So I can't stress enough. You really need to know what those words mean. And if you just associate it with long time, t equals infinity picture, steady state, you're good to go. All right. Nice job. All right. Now let's have some fun. All right. Let's keep going here. I think this one shows you why inductors are kind of this is very interesting and disturbing and fun. Okay, so let's take a look at this one here. I'm going to get it drawn up and you could start getting your brain wrapped around it. 30.25, all right? Up till now, I was just kind of doing the mechanics, making sure we got that right. Now we can start seeing interesting stuff. So this is 30.25. Whoops. Got it. Okay, so the switch is held open for a long period of time. Just bear with me on this one. Okay, just after the switch is closed, how much current is going to flow through each branch?
None through the middle, all through the right.
Sounds good to me. Because the inductor is going to act like a brake. Right? It refuses to allow current flow for that split second. Initially, there was no current in the 0 minus. So in the 0 plus, the inductor acts like a brake. I equals 0 for that branch. So then if this is E and this is R2, what is the current over here through R2? What is it? E over 9R, I think. Because this one's 9R and this one's R. So far, so good. What is the time constant for the inductor as it's energizing? Sneaky, huh? Well, let's remind ourselves, what is tau? It's L over resistance. If you have a large resistance, you're never going to get that much current. It's easier for it to reach that. Tau is smaller. If you have a large inductance, that's lots of coils that really opposes things. It's harder to reach max charge. That increases. So this makes sense that resistance is on the bottom and inductance is on the top in some sense, hopefully. What resistance do I use? R1, R2, do I add them? Do I put them in parallel? What do you think?
I feel like it would be just R1
Why do you think that?
because R2 is in a separate loop and
Exactly.
you're not adding them together.
So remember, this is like one light bulb in your house in parallel with this other branch. And so this branch has not, right? This, if you just did KVL on this loop, it's as if this loop doesn't matter at all. So if you have circuits in where all the different branches are in parallel, you could think of this circuit as being all by itself with that battery. Nice job. Does that make sense, everybody? Ignore this branch for the time constant. Why? Because it's in parallel, and these things in parallel have the same voltage as the battery, which makes this its own loop. So in this case, it would equal L over R1 while charging. Okay. All right. So now what's next? What energy, part C, what energy is associated with the inductor in steady state? Oh, okay. So in this case, how do I get the energy? 1/2 mass times velocity squared. Inductance is like mass, current is like velocity, moving charge. So it's kinetic energy. The inductor is like the kinetic energy. All right, so in this case, I have 1/2. I know what the L is. What is I going to be in the steady state? For the inductor's I, which current would that be? I think it's just E over R,
It's
right?
E over R, yeah.
Yeah. So that's going to be L E squared over 2R. Got it. What are the units of this puppy? Clearly joules. Here's something weird, right? You guys don't probably think about this much, but I know that a second is a Henry per ohm. Otherwise, you could think of an ohm as a Henry per second. Or you could think of a Henry as an ohm second. So these time constant equations give you an interesting way to think about the units involved with these things. So I don't know if that helps, but yeah, whatever. So you, wait, did I screw something up here? What did I screw up?
Yeah, it should be R squared.
Yep, right there. That should be squared right there. Sorry about that. Got so excited thinking about my ohm seconds and Henrys per second. Whatever. Yeah. So don't forget, you could use the time constant equations to check units in very difficult problems. You'll see this later on. All right. Part D asks about magnetic flux. Now you may be saying, dude, I have no idea. I'm just going to think for a minute. If only I had an equation that talked about this. Turns out there's the definition of inductance, which I haven't really talked about yet. Inductance is defined as magnetic flux per unit current. Sort of like capacitance. Where was capacitance here? Capacitance was related to charge per unit volt. right? Capacitance is charge per unit volt. Where was that? Inductance is defined as magnetic flux per unit current. All right. So don't overthink it. Part D just says L is equal to magnetic flux per unit current. Well, I know the current, I know the inductance in this problem, and so rearrange them. So this clearly has units of Tesla meter squared, right? Magnetic flux is B times area, Tesla times meter squared. There's some weird units that show up. Sorry, that was a little off there. Some funky units. So clearly, Henry volt per ohm is, or well, I guess that's a Henry amp. A Henry amp happens to be a Tesla meter squared. Whatever. All right. Oh, I lost my page. So that's part D. Don't overthink it. It was just a reminder to tell you that equation. All right. So it's on the equation sheet if you need it. Where were we? All right. E. This is where it gets fun. Okay. So at this moment, we now know this picture. So at the end of state D, I'm just going to draw it because it's going to be reopened. So we need to start all over. So 30.25 D. Here's the circuit at this state, just before reopening. So that's this part. I think there was an inductor. Where was the inductor? Sorry. Was it resistor then inductor? Sorry, I keep losing my page here. Should be careful. Ah, shit, I just drew on my curtains. All right, whatever. R1, L, R2. And so this is the T equals 0 minus picture now, because we're going to reopen the switch, right? Okay, now watch out. I just want to point out there's current here, and this is E over 9R, and there's current flowing this way, E over R. So the current is flowing in each branch, right? There's less current here because this is a larger resistor. What's going to happen when we reopen the switch?
The inductor will keep pushing current down, then up the right resistor.
Okay. So this is R1, R2. The inductor preserves which current? Remember what I said, the wording. Inductor preserves its own. It doesn't preserve something else. It preserves its current, not somebody else's. So what's the current?
E over R.
E over R. And notice this one has nothing to do with it. It's a decoy. The inductor says, I say what happens here. I'm the one that controls current flow. I'm the one that's energized. I'm the source of energy. I'm the battery now. Except it's not a battery. It's a current source. So instead of a voltage source, this is acting like a current source. Now let's see what the consequence of this is. If the current is E over R, all All right, let's see what happens to the voltages. Okay, so what's going to be, if the current is E over R, what's the voltage across R1?
It's E.
E. What's the voltage across 2?
You have a scary grin on your face right now.
Yeah. What's resistant? Yeah, so what? How much current flows through R2?
Just E over R?
So what's the voltage across 2?
E?
No.
Oh. It was R2. My bad.
Yeah, what was R2?
9R.
So
9E.
9E. See why I had that evil grin now?
Yeah.
So wait a minute. What's the voltage across the inductor then?
Wouldn't have to be 8?
10E?
10.
10. Oh.
Because it's providing for both. It's
oh.
I just want to point out the simple act of reopening the switch jacked up the voltage by a factor of 10 because the inductor says, I'm keeping the same current flowing. I don't care what you throw in my path. I don't care if you try to unplug my vacuum cleaner. I want to keep the current flowing. I'm going to cause a massive, massive spark when you pull the plug out of the vacuum. That's what this is supposed to be a model of. Isn't that crazy? It's not quite the same, but it gives you an idea of how these things might happen. Current sources are very different than voltage sources. And so the inductor is really a current source. When you pull the plug on this power supply, in order to keep the current flowing, it's going to have suddenly have this, right? You're trying to get rid of the magnetic field in this coil of wire. And it's like, hey, I'm going to keep it going. So I just find that very interesting that this happens.
Is there a specific reason which way the current flows from there?
Say again?
So like the current flow from like out in the second loop?
Let me put it this way. You had this current in here. So depending on the way this is running, you've got a magnetic field this way, and that's got a lot of energy associated with it.
Oh,
when you flip the switch, it's going to keep that field there. It can't instantly disappear. And so the field has to, and because it has to keep going, this has to keep being this way, which then forces this one to reverse direction dramatically. And the only way that can happen is if there's a dramatic voltage spike. Otherwise, conservation of energy isn't valid. Now, it's not like you're getting something for free. What's the new time constant? How much resistance do we have in the final state?
10R.
And so notice the time constant goes down by a factor of 10. And so the voltage jacks way up. You get this huge voltage spike, but it's going to dissipate extremely rapidly because there's so much resistance. Cool? Isn't that weird? Let's go see if there's anything else in here to talk about.
I have a question. I'm trying to think about it. So not much would change if the opposing current, so that E over 9R, if that was much greater than that E over R.
Yeah.
So if it was 9 E over R, it would it looks to me like it would just be the same. Or
yeah, if it was 9 billion, right? Now here's the deal. Okay. Every loop has some inductance, and this outer loop would have some inductance as well. So this is right. What we're assuming is the amount of inductance in this loop is negligible, but even just this outer loop has some inductance. So there would actually be a tiny bit of inductance here, which would cause this current to be preserved slightly, which would then actually partially cancel out this one. However, if this inductance is negligible, we wouldn't really notice that. The other thing that's complicated about this is switching times and the speed of light and information about electric fields. information about electric fields propagate through the wires at the speed of light. So on the order of nanoseconds to get around the information. So when you open this switch, the current in this branch, if there's truly negligible inductance, would basically go to zero in the order of nanoseconds. Whereas this current will persist on the order of 5 tau. So if the inductance is large enough, this current will not instantly change, even though the battery has disappeared. And this is not a violation of physics. It's just conservation of energy. And that energy takes time to be dissipated throughout these two resistors, right? There's energy stored in the inductor's magnetic fields. All right. So, yeah, it's very complicated in a real circuit that you would build, because every real circuit has some inductance. It's never ideal like this. Is that okay? Is that addressing your question or not?
Yeah.
Yeah.
It's interesting.
And so, in fact, every real circuit might look a bit more like this next one down here, where every branch has got some inductance in it. And this gets very tricky. And this is the one that I was showing you. If you literally have the same resistance and same inductance in each loop, then what happens is the current in each loop essentially stops instantly, because one of them is trying to keep current flowing clockwise in the loop, and one of them is trying to keep it going counterclockwise. And I'll just say, take a circuits class to learn more. And so you could still do parts A and B, but this is where people start to lose it. Okay. And so, and yeah, let's just leave it at that. Take a circuits class to learn more. Now let's go back. Rye, is that okay on that?
Yeah.
All right. And then, all right, let's see if we forgot anything. We did this. Okay, energy is the inductor. I think you could do that. And what's the voltage across? We talked about that. So we did part G, and I think I'm leaving part F for you to do on your own. I think you could do that pretty easily. Now that you know the T equals 0 plus picture, you could do the T equals infinity picture pretty easily. There's no current at all after a long time, because the switch is open and the inductor loses all its energy. So from there, you're off to the races. So let's read this comment here. I don't like to read, but yeah, let's look here. Okay, blah, 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 blah. Flyback diodes. So, all right, so let's just see what happens here. Now, I don't know if you guys know what a diode is, but I'm going to show you anyways. Okay, diodes are not on the test, but I think this can help you understand what this is. So a diode looks like this. Okay, this is the circuit element for a diode. The arrow and the wall are supposed to indicate current can flow this way, but not that way. So it allows current to flow in one direction. Has negligible resistance. It's got there's a little bit of a voltage drop across it, but usually we ignore these things and just assume it allows current flow in one direction. So now in this case, let's say we had this same circuit. All right, and then we're going to reopen this switch. Whoops, I think there was a resistor here. Let's just draw the circuit first. And now, remember, we had this circuit going, and there's a large current right now going down this way. Okay, or there's some current flowing this way. So what we could do is we could put a diode in parallel with this thing. Like this. Now think about this. The wall is pointing this way. So current can't flow this way. It hits the wall and craps out. So there's no current flowing this way. All right. So in this case, I'm not going to get any significant current flowing this way unless I exceed the breakdown voltage of the diode. Oh, yeah, right. Well, this makes sense. Yeah, right. Okay, so now take a look here. The idea is pretty simple. When current's flowing this way, the diode basically has no effect on the circuit. Current just flows right through this and blah, 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 blah. What happens if I reopen this switch though? Now it's really easy for current to take this path instead of having to go through that resistor. And so the current can loop through here and you won't blow out, you won't have this huge voltage spike, right? Because the current has somewhere to go. And you could throw a small resistor in there to keep things from burning up if you don't want your diode to get too hot or something. But essentially, you could just throw that diode in there, and that gives the current a path for this inductor to discharge. I should be careful, de-energize, right? So you could de-energize the inductor this way rather than having to go through this huge outer loop. So if you want, you could read about flyback diodes, and you could get pictures of Tom's fried circuit solenoids here. But yeah, that's the idea. If you have a large inductance in your circuit, if you have a motor, or if you have a solenoid or a relay or some kind of circuit where you have a lot of coils of wire in there for some reason, you may want to consider putting in a flyback diode to keep the circuit under control when you close this or when you try to turn it off. All right. Cool. All right. We're almost time for a break here. Let's finish this out really quick. Here's the other kind of problem you could do here. So I don't really like my grid lines here, but whatever. You could deal with it. So it's just not the prettiest. So notice, don't forget that you also need to know how to do these problems with graphs. So we did a bunch of this in the RC transient lab. So hopefully the idea is you could identify, aha, this would be I initial. And we could see that I at time infinity is about 5. Don't forget to read your units, nanoamps, and oh boy. So this is going to be great. Right. And so then remind me, if you want to learn about the resistance or the inductance, what's something you might do with this plot? Let's scroll down and read the question here. I know you're tired. We're trying to get the potential difference across the battery and the inductance. Any ideas what you might do?
Probably find tau and do
How
some
would you get tau?
inductance. You know where, is it the same where you find like 5 tau is about 100% and then divvy it up?
You could do that, but that's very difficult to tell when you exactly get to 100% here. So that's a correct strategy, but it's difficult to use. That would get you approximately right. What else could you do?
Halfway up.
Halfway up. So
Yeah.
right around in here, this is a point that looks pretty clear to see. This is a point that looks pretty clear to see. Do you see how those 2 points pretty much line up on the grid? And then you write your I of t equation, right? But how do we get the potential difference across the battery? This is an I plot. Let's scroll down and look at that a little more. How would I get the potential difference across the battery?
Isn't the potential difference just I times R?
Okay, so there's the claim here. Let's see if this works. I'll just do it on screen. So she's saying, isn't the current, oh wait, you said, isn't the voltage just I times R? That's true for the voltage across the resistor. So under what circumstances will the voltage across the resistor happen to equal E?
At the max time.
Yeah. So at t equals infinity, J is exactly right. So you just say, well, at t equals infinity, go grab the current up there. I think the current at t equals infinity was, what was it, 5 nanoamps? So you could say, okay, at t equals infinity, I plug in this. I know the value of R because it's right there. and then that gives me E. Nice job. And then how do you get the inductance? That was that thing we were talking about where you pick a point and you use your I as a function of time graph, right? I as a function of time is equal to, clearly this is going to be I max times what? Is it e to the negative t, or is it 1 minus e to the negative t? When it goes up like this, is that exponential decay or asymptotic rise?
Asymptotic rise.
Yeah, so I need the 1 minus e to the crap, right? And so we know I max. I'll call that I max there. So we know this is 5, right? T is a number I can read off the graph. I of t is a value I can read off the graph, say 3. And so if I plug in this value, and this value, I should be able to get an equation where tau equals some crap. And tau is L over R. I know what R is. I should be able to get L. All right. Okay. So I'm going to let you guys, don't forget you have to be able to read graphs to do these problems as well. So that's kind of the ways I might mix this up. We've been talking about RL transients. So just kind of to summarize this stuff, and then we'll take our break. Thanks for toughing that out, people. Transients. So RL transients, we see there's the standard I as a function of time, or U as a function of time. I guess you could also get voltage across a resistor or something as a function of time, or you could get voltage across the inductor as a function of time. You could also do power dissipated by the resistor. Oh, geez. Right. And remember that these are the ones that I'm underlining in red. Those are the ones that you could use your X equation on. These two you can't. And then what are some things we've seen ourselves solve for? You could solve for T, L, R, something like that. And then you must be able to read graphs. And then also you should know the T equals 0 plus and T equals infinity. Whoops. You have to know how to draw these pictures as part of that. And so all the questions that we've been working on, we're basically working on some subset of this whiteboard, right? So these are all the types of RL transient questions you could imagine. Some kind of graphing question or a steady state circuit question. What's the current or voltage across an element? Yeah, which is this pictures. And then solve for T, L, or R. These are the most common things to solve for, I guess. But yeah. I guess you could solve for, we saw one where we had to solve for the voltage across the power supply just a second ago. Things like that. Other questions while I got that up here, or not too crazy? Just going to see. I think that's the last one I wanted to talk about. Okay, so you guys could practice this one. And that was it. Yeah. Let's take a 5-minute break. Come back. We'll do a couple more problems. We'll work on LC oscillators, and that's it for tonight. Okay. So take a quick break. Take an 8-minute break or whatever. So 6:14, come back. Okay. 9-minute break. 6:15. It's only water. I thought that might be fun for you guys. Any questions while we're on break? I'll get a simulation ready. It's going to take me a minute. Any questions, anybody? We still have a couple minutes. Oop, something in the chat there. Right on. Less than a month to go and you'll be done. Holiday Wednesday, no class Wednesday. You can try to catch up or take the day off. I'll look at the quizzes afterwards. I wasn't sure if I should have done the magnitude on that one or not. Yeah. I thought it was good to make you guys think about the numbers on that. I don't think I made any typos in that quiz. You know what was really nice is after I finished your finals, I just finished your finals. I've been working on them since day one of the semester, and I just finished now. So insane. And I actually had time to proofread the quizzes, and I started going backwards from the end. So I actually was able to catch a couple of my own typos before you guys got to them for the next two quizzes. Anyways, so that's a good thing. Can I just get a black hole and do some Yeah, you just want to do relativity, huh? Yeah. Let me see something here. Yeah, I'm ready for this semester to end too. I don't know. I'll look at something else really quick here. Well, I tell you what, it's time to get going. So we have 20 minutes, and if we do it right, we can actually get something done. So let's we'll talk about we got 20 minutes to be yeah, let's get one more problem done while we have time. So let me get back into it. Okay, so up until now we've been talking about inductors and capacitors separately. All right. So if you could have page 195 open in the workbook, page 195. All right. And in particular, I'm going to start with a simulation. Hey, once you transfer, D's mean degrees, right? All you got to do is get there. You'll be all right. Let's focus on this simulation. Here we go. Take a look at this. In this case, what I'm going to do Yeah. Okay. So in this case, I'm going to close the switch. Notice this switch over here that I'm wiggling is open. So the inductor is out of the loop. When I close this thing, nothing crazy. We expect a current flow and the capacitor should charge. All right. So that was very rapid. Now I'm going to open this up. And now I'm going to close the right switch. Forget all the words on the page. What do you think is going to happen when I close the right switch? Again, the battery is out of the circuit, right? This thing's not even in there. So this battery has nothing to do with it anymore. When I close this switch, which direction will current flow?
Clockwise.
Okay, and how much current will flow initially?
None.
None. So we expect the inductor will preserve its current. What does the capacitor preserve? The capacitor preserves its voltage. So the voltage on the capacitor is still going to be, what was this battery? Let me, hold on. The battery was 9 volts, right? So in this case, do you agree that the voltage across the capacitor is going to stay at 9 volts initially?
Yeah.
So nothing is wrong here. This does not break any laws of physics. The capacitor preserves its voltage at 9. The inductor preserves its current at 0. Gradually, however, there's a tiny amount of resistance in this wire, but let's assume it's pretty negligible. So eventually the current should start to flow, right? And eventually you're going to have a large current flowing through the inductor. Eventually. At that point, the capacitor should be very close to discharging, right? So then what's going to happen? Can that current stop instantly?
No.
No. So what will
Okay.
happen to the capacitor? Let's watch and find out. Okay, think to yourself, what should happen? Initially, no current. Now it's starting to go. Remember, the electrons are moving opposite the direction of current flow. Look at that, the capacitor discharged. What's happening to the capacitor now? It was at negative 9 volts. Let's watch it again. It's taking a while, but there it goes. Now there's maximum current right at that instant. And it keeps changing back and forth. Let's see if we could change the value. Let's start this over for a second here. Let me pop this switch open here. Let me get this guy back to full charge. If we wanted this thing to oscillate faster, all right, now we've got this fully charged. What do you think I should do to the inductance? Do you think I should turn it up or turn it down? What do you think will make this oscillate faster if you had to guess?
Probably down.
Okay, let's find out. Let's try running it again. Looks like you're right. It's running a little bit faster, right? What do you think would happen if I change the capacitance? Should I make the capacitance larger or smaller to make this thing oscillate faster?
Smaller, right?
Let's find out. On the next oscillation, I tell you what I'll do here. Let's just do this. There we go. We'll make this smaller. So now I have a smaller capacitance. There's less charge built up. It should take less time to discharge. So let's see if this is also true. Here we go. Let's open up this one so I don't forget. So now the battery's out of the circuit. When we run this thing, hopefully it happens pretty quickly. And it looks like it is happening a little bit faster. So we see that the values of L and C somehow relate to the oscillations that we see. You could think of this as the capacitor storing energy in a spring and the inductor being kinetic energy. So you could think of this as being K 1/2 kx squared. And you could think of the energy associated with this being 1/2 mv squared. And it's very analogous to a mass on a spring, right? And what happens is there's some equilibrium position. And if you stretch it, you store energy in the capacitor or in the spring potential energy. And then once you let it go, at the middle, there's no spring energy. There's no charge on the capacitor, but it's all kinetic. Now, if I write the energy equations next to this, we see, if you identify the spring constant as 1/c, and if you identify x with charge, current would be the derivative, and all of this makes sense. And so this is the analogy of motional systems. And so there's probably a lot of mechanical engineers in this class, or maybe civil engineers that need to worry about earthquakes. All of the math that we've done all semester with these circuits is identical to the oscillatory systems that you learn about in Physics 162. Isn't that cool? I mean, you could say a lot of things about this class and how boring it is, but this particular aspect is pretty darn interesting. And all the math tricks that you learn to deal with circuits will directly help you understand oscillations. Does anybody, okay, so maybe I told you this already. Voltage is EMF, or electromotive force. So voltage is like a force. Now, the derivative of current would be like acceleration, but we don't really use that too much. But maybe you know this. The voltage across an inductor is defined by L di dt. Well, wait a minute. That's just Newton's second law. Force equals mass times acceleration. Isn't that cool? This analogy just keeps going. It's really fun. Where's another one for here? What's the drag force? Does anybody know what drag force is? Does anybody remember a model for drag force? Do you remember sometimes we said it was BV? Force equals, well, actually, force, okay, so this is the force equation, right? So the equivalent of force is voltage. The equivalent of velocity is current. What do you think the drag constant is? V equals I
Resistance.
resistance. So we got to be careful here. This is drag, R, and this is resistance. So the resistance in a circuit is like the drag coefficient, right? So if you want to talk about damped oscillations, we could take this out. All right, this is getting pretty heavy here. Watch what happens here. Let me pause this for a second. That's pretty close. Let's charge this up, start over. Right? What if I split this junction here and stick in a light bulb? When I do that, that's like adding some drag, right? Resistance is like drag. So now if we run this thing, I'm just going to get this out of the way for a minute. So when I run this, okay, we get maximum light there. But what will happen is over time, the capacitor will start to discharge because it's giving up its energy to the drag force, so to speak, or the drag force is dissipating some of that energy. So notice now there's no more voltage across this thing. Whoops. All right, so let's put this on here. And we see that the voltage is pretty close to zero. It's still oscillating, but not enough to make the light bulb light up or be noticeable. All right, so that's what I wanted to learn about a little bit. And let's look at the equations of this. Or any questions while I've got that up? Any questions from anybody on that? Just kind of conceptual, anything? Right, okay, let's take a look at the, I think it's really cool. I don't know why. I just think that's neat. Let's look at a blank white page of a workbook. Jeez, what page were we on? There we go. LC oscillators. So these circuits are called oscillators, LC oscillators. The most famous one is used as a radio circuit, right? They oscillate a certain frequency, so you could tune an inductor or a capacitor to a certain radio station, and then what will happen is the radio station waves will come in and you could detect it. So energy stored in the capacitor is this stupid equation. Great. Energy stored in the inductor is this, and this happens to be, I should be clear on this, omega naught is sometimes called omega resonance. It has to do with the resonance angular frequency. So it's an angular frequency. Just like we had F and omega and period, we're going to have all those symbols again. So that's angular frequency. What are the units of omega? Do you guys remember? Look at it. What do the units have to be?
It's radians a second.
Yeah.
Radians per second. Now you could say, is it just 1 per second? That's technically F. So just be aware. Remember, omega is 2 pi F. And so technically the 2 pi are radians. So we say that F, the units of F are hertz, which is 1 per second. In some books, sometimes you'll see this written as seconds, to the -1. These square brackets here, again, I just mean the units of, all right? So the units of frequency are inverse seconds or hertz. You could remember that because the German word for heart is Hertz. So you could think of a heartbeat has 1 per second approximately. That's how I don't know, or you could just not remember that. But yeah, just be aware there's a subtle difference between radians per second and seconds to the -1. This is going to be hugely important for the next 2 weeks. Okay. All right. So now I just want to point things out here. Oh, chat. Let's see. Yes, physics hurts. 1 time per second all day long. All right. So now I just want to point out here, these plus or minus signs, we can go into that a little bit. Basically, depending on which way you choose to charge these things, for example, in the circuit that we had going here, which one of these equations applies? Well, let's go look at it. I'm basically saying it's either going to be a sine or a cosine oscillation, and I either need to use plus or minus. So it depends on how we initially charge our circuit. Let me show you what I mean. Whoops. Let's go over to this one. Let's get this thing out of here. We'll just go back to this. Okay. So in this case, right now, if I see this one, the capacitor to me looks like it's going to be the voltage source. So depending how you want to do this, I would say, might as well say Q is positive EC, right? EC is from the battery, Q equals VC. And then is it going to be times cosine or sine? What do you think? If I wanted to describe the voltage across this as a function of time. Sine starts at 0, cosine starts at 1. Which
Cosine.
one seems, yeah, cosine. So that's all I'm trying to get at here. Basically, if you have something where it starts out with all the charge on the capacitor is probably going to use a cosine function because this means when time is 0, you get charge on it. All right. So if it was flipped the other way for some reason, whoops, let me see if I can get that person in here. There we go. All right. So when I run this thing, there we go. So the idea is it starts to look like a cosine function. And so that's what I'm trying to say right here. This function represents that voltage as a function of time. All right, let's clear all this and go back. And let's go ahead and put this on there. All right, there we go. Let's go back to here. And so if the capacitor is initially uncharged, use sine. If it's initially full charge, use cosine. And then it's pretty easy to get the voltage oscillations, all right, from there. Okay, so if you have a current oscillation, right? So in the inductor, it's going to relate to this. Again, this relates to the plus minus sign that you chose with the capacitor, etc. And yeah, so I should be careful here. I should be careful. Basically, the idea is if the current is initially 0, use the I. If the current is initially at a maximum, use this case. And I'll show you that in just a second. All right. And these two are related by this equation right here. So if you figure out the charge oscillations, you could just take a derivative and you should get the current oscillations. Now, sometimes you do have to think carefully about the plus minus signs. I'll just leave it at that. All right. Let's go look at a problem to work out here. There's a bunch of words about phase angles. We'll come back to that in just a minute. If you care about these phase angles, basically the phase angle relates to the initial conditions. More on that in a minute. So let's look at a problem here. Let's look at LC oscillator number 1. This is very similar to what we just had. What we could do is, we're out of time. we'll pick up here next time, I guess. So this will be next Monday after your next quiz. Yay. But at least we finished chapter 30, which your next quiz covers. So the idea is we'll pick up here next time. But if you want to, you could try and walk through this and just follow the first one as an example. And I just want to show you there is a way you could do this where the inductor is actually starting out with the energy. And all I'll say about this is notice this special switch. Okay. And it says something about this here. Imagine if you had a sliding piece of, like a piece of metal like this and another piece of metal like that. The idea is if you take your switch and slide it across, it will make contact with this point at the same instant it lets go of that. And so if you have this type of sliding switch, you can actually have the inductor maintain current and not have a break in the circuit when you do the switching. So this is how you can handle those special kinds of switches to turn an inductor over to a different loop. And it's this special sliding switch. All right. So if you want, you could use this one, follow it through, and then shocking, you use the same numbers. It doesn't produce the same results if you use it. Yeah, anyways, I'll